There are things in this universe that seem to move faster than light, waves that ripple through reality, not in space, but in something deeper, space-time itself. And what if I told you that two particles can communicate instantly across galaxies? Today, we'll journey deep into the strange and beautiful world of quantum physics, space-time, and a phenomenon Einstein once called spooky action at a distance. Albert Einstein gave us the theory of special relativity, which declared that nothing, no object, no particle, no signal can move faster than the speed of light in a vacuum, 299,792,458 meters per second. This speed limit is woven into the very fabric of the universe. It's not just a speed, it's a boundary between cause and effect, a wall that separates what is now from what could be. But then, we discovered things that don't quite obey this rule in the way we expected, things like wave fronts, entanglement, and even the very expansion of space itself. To understand how this is even possible, we have to talk about space-time. Einstein's general relativity taught us that space and time are not separate things. They're one continuous fabric called space-time. Imagine it as a cosmic rubber sheet. If you place a heavy object on it, like a star, it bends the sheet. Planets and other objects move around that curve, not because they're being pulled by a force, but because they're following the shape of space-time itself. Light travels through this fabric, and its speed is constant in that medium. But what happens when the fabric itself moves or warps? Are there things that move faster than light? Let's look at a few examples. The expansion of the universe. The universe is expanding. Not into something, but space itself is growing. Some galaxies are moving away from us faster than light, not because they're zooming through space, but because the space between us is stretching. This doesn't break any physical law. Why? Because they're not moving through space faster than light. Space itself is growing, and that's allowed. Phase and group velocities in waves now. Here's where things get trippy. Imagine a wave, maybe light or even a quantum field. There are two speeds we need to understand. Phase velocity, the speed at which a single point on a wave, like the crest, moves. Group velocity, the speed of the actual information or energy being carried. In some systems, the phase velocity can exceed the speed of light. But don't get too excited, this doesn't transmit information, and that's why it doesn't break Einstein's rule. It's like a shadow moving across a wall. The shadow might move faster than light if the source moves quickly enough, but no information is traveling at that speed. But now, let's dive into something even weirder, quantum entanglement. In the quantum world, particles don't have a definite position, speed, or spin until you measure them. They exist in a superposition, a cloud of possibilities. Now, imagine we take two particles, say electrons, and we entangle them. That means their quantum states are linked no matter how far apart they are. If you measure one, the other's state is instantly known. And here's the crazy part. Even if they're light years apart, the effect is instantaneous. This seems to violate the cosmic speed limit, but does it? Why entanglement doesn't violate relativity? Einstein hated this. He called it unspooky action at a distance, because it seemed like one particle was telling the other how to behave instantly. But there's a catch. No usable information travels faster than light. You can't use entanglement to send a message. You can't say, "Te hello," across the galaxy using entangled particles. Here's why. The outcome of measuring an entangled particle is random. Only when you compare notes later do you see that the outcomes were correlated, and that note-taking communicating results still requires normal, slower-than-light communication. So while the connection is real and instantaneous, it doesn't break causality, but it hints at something deeper. What's really going on? Here are a few interpretations physicists debate. Non-locality. Some interpretations say the universe is non-local, that particles don't really exist independently in space. They're part of a larger wave function that extends across space-time. So when you measure one particle, you're not affecting it at a distance, you're just updating your knowledge of the whole system. Hidden variables, Bohmian mechanics. Others, like physicist David Bohm, propose that entangled particles are guided by a hidden, non-local pilot wave. This wave could carry instantaneous information. This idea preserves determinism, but it requires us to give up the idea that space-time is the ultimate arena. It hints that reality may be governed by something underneath space-time, a deeper level of the universe. The holographic principle. Some modern theories suggest space-time itself is an illusion, a projection from a deeper quantum structure, like a hologram. In this view, the connection between entangled particles isn't across space, because space is just a construct. They might not be far apart at all. In this deeper reality, they could be right next to each other. Is anything truly faster than light? So, are waves faster than light? Waves, like phase waves or metric fluctuations, can appear to move faster than light, but they don't carry information. Space-time itself can stretch faster than light. Quantum entanglement connects particles instantly but doesn't send signals. Nothing with mass, energy, or information moves faster than light through space. So while the speed of light remains the ultimate speed limit, the universe is full of phenomena that skirt the edge of that rule, phenomena that hint at a reality more profound than our everyday experience. We are just scratching the surface of quantum gravity, entanglement, and space-time. The strange behaviors we observe may not be loopholes, they might be windows into a new theory, a theory that merges general relativity and quantum mechanics. Something like string theory, loop quantum gravity, or a yet undiscovered framework that redefines reality itself. The deeper we look into the fabric of space and time, the more it seems like reality is not what it seems. Maybe one day, we'll learn how to truly ride those waves, not just of light, but of space and time itself. Keep your mind open and your eyes on the stars.